find limits is just to use a spreadsheet and compute these different values. Another way to find limits, if you have an easy enough function, is just go ahead and plug in a number. Okay? So this example right here, I can just plug in 3. And why do I know I can plug in 3?
Because the limit approaches 3.
Because the limit approaches 3, but also, why? Just because the limit approaches 3 doesn't mean you can always just plug it in and get it. There's a special rule for this. There's a special word. Starts with a C. Continuous. Okay. This is a polynomial, and all polynomials are continuous everywhere. And if you have a continuous function, then you can just plug in whatever number straight into that. Okay. So as long as the function is continuous at that point, you can just plug it in. That's all I did here. 3 cubed is 27, minus 3 is 24, plus 2 is 26. So this is the limit in this case. All right? Now, you would want to do that here, but you can't. And why can't you? Because if you plug in 3 here, you get 3 minus 3 is 0. You're dividing by 0. That's undefined. Okay? Does this mean that all hope is lost? No. In fact, you can factor the numerator. And the denominator gives you a hint on what you need to factor out. You can factor out an x minus 3, and then cancel the x minus 3s. And so the limit of this is going to be equal to the limit as x minus 2 of x minus 2 as x goes to 3. So that should not be was it plus 2? Yeah, x plus 2, so there's 5. Okay? Here's a picture of what that looks like. The function f of x equals x squared minus x minus 6 over x minus 3. You should go ahead and plug that into Google. It'll graph it for you, and it'll look something like this. It's going to look just like the line y equals x minus 2, but there's going to be a hole. You may not even be able to see it on Google, but there's a hole right there, and if you try to plug in x equals 3, it'll tell you it's undefined. Okay? So, does this have a limit? Yes. Is it defined at the point x equals 3? No. Okay? If I were to stick in a point right there, would it be defined there then? Like, would it be x equals 3? Okay. So a lot of you ask, what is continuity, or what is the book trying to say when they define continuous functions? Continuous functions are like this. We say that we say f is continuous at c if the limit as x goes to c of f of x exists, and it's actually equal to f of c. What they're saying when they write this thing down symbolically is they're saying not only does it have a limit, but its limit is equal to its actual value. So f of 3 is actually equal to 5, and the limit as x goes to 3 of f of x is equal to 5. That's what we're trying to say when we talk about continuous functions. In grade school, you learned that continuous functions were ones where you could draw them without lifting up your pencil. Okay? You can't draw that function without lifting up your pencil because there's a jump, or there's a little gap. Okay? But if you, this one you could, you just draw a straight line. That make sense? If there's a hole that can be plugged up by a plumber, then it's a removable discontinuity. And the reason we call it removable is because you can plug it up. Okay? So removable discontinuity equals hole that can be plugged or fixed. Okay? What's a jump discontinuity? Was this a jump discontinuity? No. No. Can I patch it? Plug that in, it's now it's continuous. Even though there's a little v there, it's still continuous because I don't have to pick up my pencil. about this one? Is it removable? No, I can't just plug that hole up, right? So this is a jump discontinuity. So a picture's worth 1,000 words, and this picture pretty much tells the whole story about continuity. Either you have a removable one, which means a plumber can patch the hole up, or you have a jump discontinuity where no matter what you do, you can't fix it by just plugging in a point here. You have to do some type of jump. And I guess there's one other type of jump discontinuity, and that's when it does this. Okay. It goes off to infinity, and then jumps, it starts at negative infinity, it goes off that way. Okay, does that make sense? So there's a discontinuity here too, at like, let's say x equals 10. And it's jump discontinuity because I'm going from positive infinity down to negative infinity. Okay? Does that make sense? Cool. That's all I had for this. Yeah.
Can you go over that, the first one?
Removable.
Yeah, the 5,
The limit. This one?
no, all the way on the left.
Here?
Yeah. That's at 5.
Yeah.
What was it, that's at 5?
It's at x equals 3 and y equals 5. There's a hole. This function right here, if you try to plug in 3, you get 3 minus 3 is 0, so you get something over 0, and that's undefined. And that's why there's this hole. But if you simplify it by factoring, you're going to see that it's x plus 2 times x minus 3 all over x minus 3.
Cancel it off.
So as long as x doesn't equal 3, you can cancel that, and then it's going to act just like x plus 2. And so that's what the graph is telling you. Okay?
So that's how you're able to plug it in.
That's, well, no, I'm saying that if you, it's a removable one because if I plugged it in, it would be continuous, right? So I'm saying, as discontinuity, it's removable because you could plug it in. You can't just plug this in now. Well, I guess you can now. If you just plug in 3 there, you get 5. Does that make sense? Is that what you're asking?
Yeah, I don't know, I didn't really understand it.
Okay, anytime you have a rational function, if you can factor out something from the numerator and cancel that with the denominator, then once you've done that, you can go ahead and plug the value in. If you can get rid of the 0 on the bottom, then it's going to act like a polynomial and you just plug it in.
Are there times when you can't?
Yeah, like if I had something like this, f of x equals x squared over x minus 3. I can't factor an x minus 3 out of the top, so I can't get rid of that. The only thing you really do there is graph it. Yeah.
For the very first one, you said that the limit is where the lines connect, basically, for that function.
Here?
Yeah, so it would be
Yeah,
at one.
per one.
So the other closed dot above it at 2, is that also a limit?
No,
So what is that?
that's where the function actually is.
Okay.
It teleported up to 2 and teleported back down and started walking away.
Okay.
So, like, if I were to draw this function, I might draw it as a piecewise linear function. I would write something like f of x equals x plus 2 when x is less than negative 1. And it's 2, or it's, sorry, x plus, yeah, I'll write x plus 2. It's 2 when x equals negative 1, and then it's negative x when x is greater than 1. Like that tells you what's going on here.
So to solve that with the piecewise function, you plug in values to x?
Yeah, you plug in the different values and see if they match up. And you see that this one and that one would both give you 1
Okay.
when you plug in negative.
So those 3 are showing where the points are.
Yeah. But this thing is actually up there, jumped up.
Okay. That's
Okay.
always 2 then, at negative 1. You can't
Yeah.
really plug anything into
Yeah.
that.
So the point is that the limit doesn't care that it's 2 at negative 1. It can't tell you that. It only tells you what happens right before and right after. Does that make sense?
A little bit more with the piecewise. I didn't know how you wanted to label the closed dot with the 2.
Yeah, you can do it this way. So maybe we should do one more example of piecewise linear functions. Because I think people are struggling with that. Okay. So let's try and translate what this said. When you see f of x equals a squiggly bracket, x plus 5 draw what that's saying. Okay. So how do you read this?
Y equals x plus 5.
Okay, y equals x plus 5.
When x is less than 0.
Yeah, if x is less than 0, when? Okay. So when x is less than 0 is over here, right? Because this is my x-axis, this is my y-axis. So y equals x plus 5, what does that look like?
Straight line of 5.
A straight line, you plug in 0, 5,
If it can't be.
and then what? X plus 5. That's that line, right? And it would continue on over there, but for some reason I don't care about what happens when x is greater than 0. What about y equals x minus 3? So at 0 it starts at negative 3, and then it just grows with slope 1. Do I care about this stuff over here? No, because this part of the function is describing the behavior left of 0, and this part of the function is describing the behavior right of 0. Now, is this function continuous?
No.
Yes.
Yes, where?
Well.
You're both right.
Yeah.
Is it continuous everywhere?
Well, I mean, you go up to the point, it's open, but the one underneath it is closed, so it still contains that point.
Okay, but let's test this.
It's continuous on two different intervals, from negative infinity to 0 and then from 0 to infinity.
Yeah, different from.
So it's continuous from negative infinity to 0, and then from 0
Well,
to
hard,
positive
wouldn't it be
infinity.
a hard bracket for the second part?
No, because you can't be continuous if there's a jump. This is what we call jump discontinuity, because the left-hand limit doesn't equal the right-hand limit. Okay. What's the limit as x goes to 0 from the left of f of x? 5. What's the limit as x goes to 0 from the right of f of x? Negative 3. Does this equal that? No. So it doesn't have a limit at x equals 0 because the left-hand limit doesn't equal the right-hand limit. And so it can't be continuous. Okay? In this case, you'd say there's a jump discontinuity. Okay? Is that cool? What if I change this and I made this negative x plus 5 when x is greater than or equal to 0? What about if I just said x greater than 0? What would I draw? Okay? So now what's the right-hand limit? Okay, the limit's 5. Okay, so then I have left-hand limit equals right-hand limit, so the limit exists and the limit is 5. Because I can say it's both going into and leaving the scene y equals 5 at x equals 0. Okay? Is it continuous?
No.
Yeah, no.
No. Why isn't it continuous?
There's no point.
Because we haven't defined where it's at right now. It could be there, right? And then it wouldn't be continuous because there'd be a big hole. We'd have to pick up our pencil to draw that point. What if I said this?
It'd be a whole.
Yes, then it's continuous because I patched the hole. Okay? Does that make sense?
Yeah.
To be continuous, you can't pick up your pencil. Or that's the intuitive definition. You're not picking up your pencil, you just draw it like that. Okay? So that was, the book said that you're continuous at C if the limit of f of x as x approaches C is equal to the value f of C. Okay? So that means that the limit has to exist, f of C has to exist, and they have to be equal. So this is what the book called continuity. Okay? If I did this, would not have f of c equal the limit of f of x, because f of c is 2, the limit is 5, right? It's only when I plug it in and show that they're both 5 that I get conjugate. Okay?
When you write the intervals, are you using parentheses and brackets at different times, depending on whether, like on the far right, where it's x is, when x is, greater than or equal or less than or whatever?
Yeah, this would be parentheses, or this would be closed bracket because I'm including 0, and open parenthesis because you can't include infinity.
Mm-hmm.
And this would be negative infinity to 0. Okay? So if you're including the point, you use a square bracket. If you're not including the point, you use a curly bracket, or a round bracket. Yeah.
But on that first example on the jump,
Mm-hmm.
you didn't use a bracket because it wasn't continuous?
Saying here.
No, when you had that first,
Oh, if I did this.
Yeah.
Then I would draw this.
No, it was still,
No, it's what you
greater
have
than or
under the
equal
green
to.
f of x.
It was x minus 3, remember?
Yeah, yeah.
And then that was a closed circle because it was greater or equal to? Yeah, I'm saying, why
Yeah.
wouldn't you use a bracket because there's a jump?
I did use a bracket. I would say that from 0 to infinity it's continuous.
No, I asked you and you didn't do
No,
that.
it's right up there by your head. You see, you wrote that
Right
down?
there.
Oh, this?
Yeah, and there's no
Yeah,
bracket there.
it's not continuous here
But when it's under
because there was a
bracket.
jump. So,
That should
But
be
it
a hard
still
bracket
includes the
though, right?
point.
no,
It shouldn't?
it's not a hard bracket. It's not continuous there. So this is saying that it's continuous from here to here and from there to there.
Okay.
But what's going on there is even though that's closed, there's a discontinuity here, so I don't include it in the interval of continuous stuff. I don't count it as being
If
continuous there
there's
because
a
there's a
jump,
jump. Yeah,
if there's a jump but one of them's closed, you still don't use the bracket.
you still don't use the bracket. Even if it's closed, it's not continuous there.
Because if the other line were to close that hole, then you have multiple points in the same spots.
Right.
There'd be no point.
Okay.
Let's get to work and maybe you guys can explain this stuff to each other better than I can.